When gAIL's on.
Yes. Where'd you go? It's been a long week. It's my experience. And that's gAIL's. Where's that yours?
That's me.
Okay.
You want to put it so it's not on, that doesn't have this. Down the side, yeah.
The next meeting
Yeah.
is the Bomber game. And we'll have
Oh,
to
I
postpone
thought-
it a week. Don't moan, it happens.
I thought I checked all that, but then I
Well,
changed
somebody
the
just
meeting
looked
to
at
the 18th. Yeah, I checked on the, we
That-
can't
that
postpone
makes we're still with it.
we
Okay.
can't postpone it.
We're live now.
Okay,
If you can't postpone it, then it can't be held.
I know. We might have to go forward.
The microphone,
I need the microphone.
the wireless.
Okay, good evening, everyone. Welcome to the RASC meeting. My name's Judy Anderson. I'm the vice president and I'm filling in for Dennis Lyons this evening. So welcome to people here in person, hi, and the people online by Zoom. We're going to kick off the meeting with gAIL Wise's basics or beginner session, whatever you'd like to call it. She talks about a constellation of the month, so to speak. And this evening, she's going to be talking about Ophiuchus and Serpens. So gAIL.
I'm just going to change. Good to go. And those are working. Those are working.
Okay. So am I up? Okay. Am I on? Can you hear me? Perfect. So I borrowed this from my chat. Look at the mouse, a star, and that's the face. There it is. I need a little more light. That's good. In the southern summer sky, we see what appears to be a huge surfboard. Maybe it's a skateboard. Makes me think of Dracula's coffin, the way that the top goes like that. This is Ophiuchus, the god of medicine, who stands with a huge snake coiled around his waist. Ophiuchus was the son of Apollo and Coronis. Apollo loved Coronis very much, but she made him angry when she was unfaithful with a mortal while she was pregnant with Apollo's child. In a rage of jealousy, Apollo shot Coronis with an arrow, but just before she died, he rescued their unborn baby. He took the infant to Chiron, the wise and gentle centaur. Chiron raised Ophiuchus as his own son and taught him the secrets of medicine. In time, Ophiuchus grew to manhood. He settled down to married life. He was so skilled in medicine that he could not only heal the sick, he could bring the dead back to life. On one occasion, in Crete, Glaucus, the young son of King Minos, fell into a jar of honey and drowned. As Ophiuchus contemplated the body, a snake slithered towards it. He killed the snake with his staff. Then another snake came along with an herb in its mouth and placed it on the body of the dead snake. The dead snake magically returned to life. Ophiuchus took the same herb and laid it on the body of Glaucus. The boy was then brought back to life. After a few more similar resurrections, Hades, the god of the underworld, began to realize that the flow of dead souls into his domain would soon dry up if this technique became widely known. Hades complained to his brother Zeus, the king of the gods, who struck Ophiuchus down with a thunderbolt and killed him. Apollo was very angry at the harsh murder of his son, and he retaliated by killing the 3 Cyclops who forged the thunderbolts for Zeus. To appease Apollo, Zeus made Ophiuchus immortal. Considering the circumstances, Zeus could hardly bring Ophiuchus back to life again. So instead, he placed his image among the stars. Here he stands with his right foot in the Milky Way and his left foot crushing a scorpion. The ancient Egyptians identified Ophiuchus with Imhotep, who was a scholar and advisor to Zoser, who ruled Egypt in the 26th century BC. Let's not confuse him with Boris Karloff. This Imhotep was a real person, one of only a few to be commemorated with the constellation. He was a man of great learning, especially in medical science, architecture, and astronomy. It was Imhotep who came up with the idea of a pyramid as a burial chamber for his king. Ophiuchus is the unofficial 13th constellation of the zodiac. If you were born somewhere between November 30th and December 17th, chances are the sun was in the constellation Ophiuchus the serpent bearer. Therefore, your sign should be Ophiuchus. But of course, Ophiuchus is not an official constellation of the zodiac, and you will not find it on horoscopes. The serpent holder and the serpent are 2 large, intertwined constellations that take a fair bit of concentration to trace out their entire shapes. To the north is Hercules, on the west is Libra, Scorpius is on the south, and on the east are Sagitta and Aquila. Ophiuchus is the 11th largest constellation, but he seems a lot bigger. The serpent bearer's brightest star is Ras El Haig, which is 2nd magnitude. The name is from the Arabic for the head of the serpent charmer. Its distance is 60 light years, and it's about 40 times as luminous as our sun. The most impressive feature of the summer sky is the chain of Milky Way star clouds. In the southern part of Ophiuchus are some of the richest areas of the Milky Way, only a few degrees from the galactic center. These incredibly rich star fields are streaked by dark winding lanes. Here we are looking through the dust-streaked spiral arms towards the center of our galaxy. This gigantic dark lane is called the Great Rift, and it's the same huge dust lane that we see in edge-on galaxies. 30,000 light years beyond the Great Rift is the center of our galaxy. Ophiuchus is just loaded with beautiful globular clusters. He has 20 of them, and 7 of them are Messier objects. M10 was discovered by our friend Charles Messier in 1764. Its magnitude is 6.6, so it's very bright, and it measures 15.1 arc minutes in diameter, so it's more than half the diameter of the full moon. This one is very easy to find with binoculars if you have a very dark sky. Just about 3 degrees to the northwest of M10 is M12, another globular cluster, which is just a bit larger and a wee bit fainter. This one was also discovered by Charles Messier in 1764. It measures 14.5 arc minutes in diameter, and its magnitude is 6.8. Its brightest individual stars are about magnitude 12. You know, most people will say that M13 in Hercules is the best globular in the sky. But if you're like me, you're 5'2" and you like cats. No, I mean, if you're like me, you will say that these 2 globulars are just as impressive as M13. They just take a little more effort to find them. M9 is another small, bright globular cluster that was discovered by Charles Messier in May of 1764. In fact, he found M9, M10, M12, and 14 all within a few nights of each other, which is not really surprising because they're all so close together. M9 is one of the nearest globular clusters to the center of our galaxy, about 55,000 light years from the galactic center. This is one of the smallest of the Ophiuchus Messier globulars, but it's still fairly big. It's 9.3 arc minutes in diameter, and its magnitude is 7.6. M9 is traveling through space, and it's moving away from us very quickly at 224 kilometers per second. Under good conditions, you can just glimpse it with 10 by 50 binoculars. M14 is located in a rather blank area of our serpent bearer. Its magnitude is 7.6, the same as M9, but it appears brighter because it's smaller. Its diameter is 11.7 arc minutes, so about 1/3 the size of the full moon. M14's claim to fame is that it was the very first CCD image ever taken. M19 is an oval-shaped globular. The deformity of its shape may be because it is so near to the galactic center. It's 28,000 light years away from us, but only 5,200 light years from the center of the galaxy. It's fairly rich and dense. Its magnitude is 6.7, and its diameter is 13.5 arc minutes. Its brightest stars are about magnitude 14. M19 is very easy to find. It's just 8 degrees west of Antares, which is that bright star that marks the heart of the Scorpion. M62 is one of the most irregular shaped globulars, also possibly because it's so near to the galactic center. It's only 6,100 light years away from the center. M62 is magnitude 6.7, and it measures 14.1 arc minutes in diameter. It's very much like its neighbor M19, but its core is much denser. M107 is yet another globular cluster. I told you Ophiuchus was packed with them. This one was discovered by Charles Messier's friend Pierre Méchain in 1782. It's smaller and fainter than the others. It measures 10 arc minutes across, and its magnitude is 8.1. This one is very, very easy to find because it's right below that bright star, which is actually a naked eye star. All of these globulars are visible in binoculars, but it takes a telescope to really do them justice. Away from the globulars now, there is one galaxy in Ophiuchus, NGC 6384. This is a spiral, and we see it almost face on. It measures 5.8 by 3.8 arc minutes, and its magnitude is 10.4. It's fairly close to the plane of the Milky Way. There is a bright planetary nebula here, NGC 6572. This is a tiny bright blue oval. It's 15 by 12 arc seconds, and its magnitude is 8. There is a little asterism, an obsolete constellation called Poniatowski's Bull, which is similar to the Hyades in Taurus. This little bull's history began in the year 1777, when Abbe Punctzebuch of Wilma, a Polish astronomer, asked the French Academy to honor King Stanislaus Poniatowski, the last Polish king, with a constellation. But by the end of the 19th century, this new little constellation and its stars were returned to Ophiuchus. On October 9th, 1604, a new object, a supernova, blazed forth in the southern part of Ophiuchus. It soon reached a magnitude of 2.25, brighter than any star in the sky, even brighter than Jupiter. It was first discovered by a student of Johannes Kepler. It remained visible to the naked eye from October 1604 to March 1606, a year and a half. But after that, they could not observe it because they didn't have a telescope, and it's now called Kepler's star in his honor. In 1941, an attempt was made using the 100-inch telescope at Mount Wilson Observatory to detect the remnants of this supernova. Red sensitive plates were used since the star appeared in a densely obscured region of the sky, deeply embedded in the dust clouds of the southern Milky Way. A faint fan-shaped nebulosity was discovered at the expected position. It's about 40 arc seconds in diameter, and it has a magnitude of about 19. Slightly northwest of the top of the Polish Bull's western horn is a faint red dwarf called Barnard's star, or Barnard's runaway star. This is famous for having the greatest known apparent motion of any known star. Its magnitude is 9.5, and its luminosity is about 1/2500th the brightness of our sun. Its mass is 16% of the sun's mass, so with a diameter of 140,000 miles, that makes its density about 40 times the solar density. Its distance from us is 6 light years, so Barnard's star is the second nearest star to our solar system. There is a patch of dark nebulosity called Barnard 72, or the Snake Nebula. Its thickness runs between 2 and 3 arc minutes, and it's about 6 arc minutes long. A good view in a 4 to 6 inch telescope requires really dark, clear skies. This is part of the much larger Dark Horse Nebula. I can't see it anywhere on this picture, so if you can, you get points. This is sometimes called the Prancing Horse Nebula, and it's about 480 arc minutes across. It's very big, but you'll need a huge telescope to see it. Really, photography is the only way to bring it out properly. It's kind of tough to make it out in this picture, so I've got this little drawing for you. See his back legs there? There's his front leg. It's skewed a little bit, but I know you can see it. Serpens. The serpent is the snake that is wrapped around the waist of our serpent bearer. This is the snake that was resurrected after a second snake placed a revival herb on it before its death. It is divided into serpens caput, the serpent's head, and serpens cauda, the serpent's tail. Do you have any idea how difficult it is to find these pictures where anybody's wearing any clothes? At one time, the constellation of Ophiuchus was referred to as Serpentarius, whose name literally means the serpent bearer. In most mythology representations, you'll see Ophiuchus represented as a man wrestling with a large snake. His body represents the division of the snake, serpens, into its 2 parts, serpens caput and serpens cauda. Even though they are divided by Ophiuchus, they are still one constellation. The brightest star in Serpens is the red giant star Alpha Serpentis, which marks the heart of the serpent, and I am not going to try to pronounce this. If you are working on the Rask's double star list, Ophiuchus has none, but Serpens has 2 for you to look at. In Serpens cauda, the tip of the snake's tail is Theta Serpentis, also called Allia. This is actually a triple star. It has an overall apparent magnitude of 4.0, which is easily visible to the naked eye. The main star is magnitude 4.6, and the secondary is only slightly dimmer at magnitude 4.9. It has a separation of 22.4 arc seconds, so it's easily split with a small telescope or a pair of binoculars. There is a dimmer third component, which is magnitude 6.8. It's 421 arc seconds from A. William Herschel first observed this on October 17, 1779, but it had been seen by earlier astronomers, and the stars all appear white in color. In the snake's head, Serpens caput, we find the double star HD 144564. The combined magnitude of these two is 6.6, and the individual magnitudes are 6.9 and 8. They're separated by 38.2 arc seconds, so they're easily split with binoculars. Serpens contains 2 Messier objects. M5 was discovered in 1702 by the German astronomer Gottfried Kirch, and Charles Messier observed it and added it to his catalog in 1764. He described it as a fine nebula, which I'm sure contains no star. It's also known as the rose cluster. I don't know why, because it doesn't look anything like roses. This is one of the oldest globulars in the Milky Way. Its magnitude is 6.7, so it's just visible to the naked eye. William Herschel was the first to resolve individual stars in the cluster in 1791, and he counted roughly 200 stars. To the naked eye, M5 appears as a faint star, Binoculars show it a little bit better, and even a small telescope will show you one of the finest globular clusters in the sky. Its diameter is 17.5 arc minutes. And an easy way to find this, these are the feet of Virgo. So follow along the legs of Virgo, down the neck of Serpens, and it's right at the intersection. And M5 was my very last Messier object when I was working on my list, so it has a little bit of a soft spot for me. M16 is also known as the Eagle Nebula. This is a large cloud of gas and dust. It was discovered by Jean-Philippe Chazot in 1745, and Charles Messier recorded it in his catalogue in 1746. The nebula is named for its shape, which is said to look like an eagle with outstretched wings. It's also known as the Star Queen Nebula. Though this is not visible to the naked eye, you can see it using a small telescope or even a good pair of binoculars. You would need a much larger telescope along with very good weather conditions to see the pillars of creation. The distinctive structure of the pillars is created by a nearby cluster of massive stars called NGC 6611. The cluster associated with the nebula has approximately 8,000 stars. The brightest star has an apparent magnitude of 8.4, so that star is easily visible with good binoculars. The Eagle Nebula is a stellar nursery. It's a place where new stars are being born. It's about 7,000 light years away from Earth, and the nebula contains 3 enormous pillars glowing like stalagmites from the floor of a cave. These are called the pillars of creation, and they're made from gas and dust left over from the Big Bang, and are thrown out from previous generations of stars as they died. M16 has provided Hubble with some of its most iconic images, and the James Webb Telescope took this picture of the pillars of creation. There are a few more deep sky objects in our Serpent, and we'll look at a couple of them. The Twin Jet Nebula, known as Minkowski 2.9, abbreviated M2.9, is a planetary nebula that was discovered by Rudolf Minkowski in 1947. It's about 2,100 light years away from Earth. This bipolar nebula takes the peculiar form of twin jets of material that emanate from a central star, and its magnitude is 14.7. It's also known as the wings of a butterfly nebula, or just the butterfly nebula. The Little Ghost Nebula, also known as NGC 6369, is magnitude 12. This is called that because it appears as a small ghostly cloud surrounding a faint dying star. It was discovered by Sir William Herschel in 1784. The central star is magnitude 15.6, and the ring is about 30 arcseconds in diameter. Here is a dark nebula called Barnard 68. It was discovered by the American astronomer Edward Emerson Barnard, and he added it to his catalog of dark nebula in 1919. The cloud's mass is about twice the mass of our sun, and it measures about a half a light year across. It's both close enough and dense enough that stars behind it cannot be seen from Earth. It isn't that there are no stars here, it's just that the dark nebula blocks their light, so we cannot see them. Here is a group of galaxies called HCG 079, or Seyfert Sextet. This is similar to Stephan's quintet in the constellation Pegasus. Astronomers named this grouping for the astronomer Carl Seyfert, who discovered them in 1943. This is a Hubble image. It's extremely unlikely we'll see anything like this with our telescope. The brightest galaxy here is NGC 6027. The group is about 190 light years away, 190 million light years away, and it appears to contain 6 members, but one of the galaxies, NGC 6027d, is actually a background object. It's 700 million light years behind the group. And another galaxy, NGC 6027e, is actually the tail of NGC 6027. It actually goes like that. The gravitational interaction among these galaxies should continue for hundreds of millions of years. Ultimately, the galaxies will merge to form a large, single, giant elliptical galaxy. There is one well-documented meteor shower associated with Ophiuchus, which peaks on or about June 20th of each year. It's called the Ophiuchus. The radiant is near the Sagittarius border, and the hourly rate averages 8 to 20, so it's pretty crummy. And there are all these other showers, but I haven't been able to find any dates or rates for them. And there are 2 meteor showers associated with Serpens, the Omega Serpentids, which peaks on December 26th, and the Sigma Serpentids, which peaks on December 27th. But hopefully you have better things to do on December 26th and December 27th than to be out looking for meteors. So even though we don't get very many hours of darkness in the summer, it is starting to get darker now, and there is a lot to see in this area of the sky, especially if you like globular clusters. The end.
Presentation.
Okay, thank you very much, Gail. So I noticed that Corona Borealis is just above Ophiuchus and that we're supposed to be keeping an eye out for a definite brightening in there. I don't think anybody's seen anything yet, but they're waiting still. So now we'll begin the meeting, and I'll start with the land acknowledgement. The lands from which our members and guests are joining us are located on original lands of Anishinaabe, Dakota, Cree, Oji-Cree, and Dene peoples, and the home areas of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge harms and mistakes of the past, and we dedicate ourselves to moving forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. Okay, so the general outline for the meeting is, as you see in front of you, announcements, then what's up and what's new, and then we'll have a break, and then the main presentation before adjourning the meeting over to Boston Pizza if you're feeling like a late night snack or dinner late. There is a big glitch in the evening program. Mike Caracas was called away on a family medical emergency just as we were leaving home. And, you know, there's no decision in that kind of situation. You just have to go. He was good enough to let me know. So we doubled back, and Jay found a talk. So he's going to fill in with something at super last minute, but thank you, Jay, for doing that. Without further ado, I will start some announcements. So last weekend, was it only last weekend? No, 2 weeks ago, thank you. We had Sprucewood Star Party, which was a terrific event this year. We had an amazing walkabout with telescope equipment there. Various people. Roger came with various pieces of equipment to try out, and this is Steve with his binocular viewers and sun filters. Paul Moffat, and a homemade telescope that he's been working on for decades, literally, but is really unusual optics, plus a much more modern one. Michelle's telescope, which she also described. Mike Caracas with his, and I know he did some planetary imaging. Stan with a small Daub, which he really likes, kind of tabletop, beautiful flexibility. Paul Shelton with a scope, and I know he was doing some imaging. I think this fellow's name is Raj, is that right? And he had a super cool looking, at least, telescope, which he also was using for imaging. And he was very, very knowledgeable about every little part of it. There are many people who know a lot in our club, and I encourage you, if you're curious, you just want to suck information from somebody, just go up and introduce yourself. Nobody here has, I won't say that. I was going to say something a bit not nice. No one here has an attitude that they will not share information. Everybody is friendly and really happy to speak with you. Everybody learns from everybody else. Doesn't matter what the question, doesn't matter the situation. So please feel free to come up to anybody and just say hi. So some announcements this evening. The Lockhart Planetarium at the University of Manitoba, which is coordinated and directed, I think, by Danielle, Dr. Danielle Pahud, is having its regular session. I think that's on the, yes, Michelle, Danielle?
Yeah, we have an open house on the last Wednesday of every month at 7 p.m. It's free and the topic changes every month.
And we have to register for that on the website, or can you just?
There's an event right page where you can reserve tickets. That just guarantees a seat. There are often a few seats left, so if you want to try your luck without it, you're welcome to do that as well.
The last Wednesday. Last Wednesday. Okay, so we're approaching the last Wednesday fairly soon. The Observatory Committee has been meeting, and there's a group of people planning some repairs, hopefully to be done with good luck and good weather before the winter starts. They're also working on terms of reference for the committee and establishing it. We'll have to do some changes to bylaws if we go in that direction. The fundraising committee has been reduced by one because one of our councillors moved to Minneapolis a couple of weeks ago, but I don't think there's anything on the horizon. Wing, am I right? I don't think we have any fundraising.
Other than that, the imagine,
Oh, yes, we're fundraising a GoFundMe for Telescopes for Kids program. Thanks for the reminder on that. Every year we take applications from school children, almost preschool children sometimes, and a couple of winners receive a telescope. I think we're going to be awarding those in the springtime or late winter session. So we're fundraising for that at the moment, and then we'll purchase the scopes and put out a call for applications. The Explore the Universe program, Stan, did you have anything to add? Nothing new on that front. Telescope loaner program, Mike isn't here. First thank yous of the evening on the slides anyway are to Damon Nightshade and the volunteers for Spruce Wood Star Party. We had about 52 or so people, 54, I think, register for the evening or the weekend. And we had a stellar breakfast thanks to Wing and Doug and Damon, the 3 chefs with a heck of a lot of fortitude, making pancakes and sausages. And we had 2 great dark nights. People looked through all kinds of telescopes, walked around, talked to one another. It wasn't too cold. It wasn't buggy. It was really great. So thanks to everybody who volunteered and thanks to everybody who came. We had a really great time. Stan Runge is collecting ideas for workshops. Stan, did you want to say anything about anything in the works?
Star hopping.
Oh, right, star hopping, which is finding your way around the sky by going from one star using asterisms to direct you. Oh, sorry. Well, there's a number of people here we haven't seen before, so I didn't want to, like, nobody will sign up for a workshop where they don't even know what a title means. Okay. The nominating committee this year is Scott Young and Dennis Lyons, and they're seeking nominations to fill positions for president, vice president, treasurer, and councillors. And I know there are some people that are standing for re-election for some of those positions, or at least one. Please approach any of council and consider taking on a role in the club. It's really one of those things where this is all for by volunteers, and it really does build a great group of friends, especially if you hang in there. Some people are on their third or maybe fourth round through council, and I have to applaud their fortitude and eagerness to help others out. It's really a learning experience for everybody. The members observing night is usually the night after our regular meeting, but because our meetings have had to shift a little bit because of various events on campus and availability of this theater, often they seem to fall on the new moon or very close to it. So we've adjusted a couple of those members observing nights to avoid the full moon. So members observing night this month is going to be in a week Saturday rather than tomorrow. I should just note that one of the people in attendance has let me know that the next meeting is scheduled the night of a Bombers game. So probably I'm going to have to change that or change the location. So please watch for the invitation to the meeting. And my apologies, that's my fault. I know I checked that there wouldn't be a Bombers game on October the 11th, but that's the Friday of the Thanksgiving weekend. So it was suggested that we move the meeting. And of course, I didn't think to check again, not being a football fan too much, unless they get in the playoff. Calendars, we've ordered some, but there will be a limited supply. So please order them early, put your name in. I don't know if Stan, you want money right away? Yes? Yes, you would like the money right away? $15?
We have 25 calendars on order. That's all we're going to bring in. Outside of that, we'll have to order on their own.
Right.
We are.
Right. $15. And if you ordered them on your own separately, I think you pay almost double that. So it's really worth, if you're interested, getting a RASC calendar. And we determined ahead of time that the annual general meeting will be the 14th of March, 2025. Mainly this will be for elections and the financial reporting, which is required under our bylaws and our incorporation. And the date will allow us to complete the whole year's financials and the audit, and then present them in a polished form to you. There's two other announcements that I have. One is that there's an outreach activity on October 9th with a rain date of October 10. It's going to be held for the first time on the university campus in the evening in the area that used to be the Southwood Golf Course. So it's now called Southwood Circle. There's parking on Markham Avenue. This is being coordinated by the University of Manitoba Properties Incorporated, which is the company that is tasked with developing this whole golf course area. So they started by extending Markham up into that area where there used to be a golfing clubhouse that made all the mud and the traffic disruption to the north of this building. But now they're also thinking about what they're going to do. I know they have a plan for the further west part between University Crescent and Pembina Highway. So that is October 9, 10. It's a Wednesday or Thursday, depending on the weather. And if you would like to volunteer for that, we don't know how many people will come. It's a public event. We're excited to make this bridge with the university on campus for the public. And they will be advertising, as will we. So please see me or other people on council if you're interested in volunteering. And if you were at Spruce Woods, you will remember that we had coordinated to get some gift certificates from All Star Telescopes. We actually don't know 3 of the people who were awarded those. We have some names. Just let me get out of here and go here. We have Alan, Rohan, Michelle, and Abdul, but there's 3 more people. So please come to me or Wing Kwong and let us know if you also received one, because you didn't give your email to Wing on site. Okay? I think. Oh, that looks horrible. Sorry for that. So dates for upcoming meetings, I've said October 18th. That's probably the one that will either move or change. November the 8th will be in a room down the hall because this room is busy. And December the 6th in this theater. So stay tuned for update on that. And this is just a note for those of you who are just joining. We have a communication system so that everyone gets as few emails as we can make it from a major blast to all of the RASC members. Those are typically meeting invitations to the annual general meeting, notices of elections, and really high-end official things. The groups.io system is how we have chosen to communicate with one another on specific things like Sprucewood Star Party organizing or astrophotography, astro sketching. There's a general forum, there's an equipment list. You can ask a question to that group. If you want to sign up, this is how you do it. You go to groups.io or raskwinnipeg.groups.io/g/main. If you search on groups.io, you get to it, you can see a list of all of the groups that are there, and there are many, and you can sub-search for RASC and then join up. You join up with your Gmail email account, I believe, or another one. You put in a password, and then once you're in, then you can sign up for any and all subgroups that you would like to get emails from. And there's not tons and tons of traffic unless some event happened, like there's a big auroral storm, somebody send an email and that kind of thing. So this is so that you can read the general news from the center. And believe me, I've tried to make that font not blue many times. Hyperlinks insist on being blue in Microsoft. I think I'm going to unhyperlink them and underline them next time. Okay, this is members observing night, September 21st at our observatory at Glenlee. There's a warm room. We checked it out yesterday. Trying to see aurora. There's still tea and coffee supplies and water, and everything looks shipshape. Now the next speaker is Bryan Stach, going to give what's up for us. Here's
think we did. The, I'll just put it on here. That was it. I'm gonna pull this here, whatever. Yeah, go ahead. Work on it too. We're good. Yeah, it's right there.
Hello, everyone. Okay, we're going to talk about what's up for September 2024. There's a lot to cover, so we'll move on quickly. Okay, so what's up? Okay, that was from the Star Party. Okay, we're going to start off with the planets. So basically, Venus, Mars, Jupiter, and Saturn would be the only real planets that can be visible in the evening. The times I have listed here, again, at the end of the month, it's going to change. It'll just rise up a little earlier. So Saturn's going to set pretty early. I mean, late in the morning. Mars and Jupiter are going to be pretty high in the evening, and Venus, as we say here, in the evening twilight. So, okay. So for the September events here, we do have some unusual ones. The partial lunar eclipse is one of them. Just that because after we did have a solar eclipse not very long ago, it's not uncommon for a partial, or in our case, a partial lunar eclipse to happen. We do have the equinox happening on the 22nd. Jupiter would be 6 degrees south of the moon. The last quarter would be on the 24th. And then Mars would be 5 degrees south of the moon. Now, this is tomorrow morning. It's here. So we do have Mercury that is going to start to rise. The sun's not very far here. So just before it starts to rise, we do have Mars and Jupiter. And then, as I mentioned earlier, the next slide here, Saturn's going to set early in the morning. We do have the planet Neptune up here. And of course, if you notice there's a lot of Starlink, and this is happening around 6 o'clock. So could be quite interesting. Now, this is for tomorrow night, and I want to keep it current because things change throughout the month. Okay, so I'm going to step away because I don't think the camera's really on. Okay, so we do have the Pegasus Galaxy with the Andromeda Galaxy, or in other words, M31. That's another bright object. At the observatory night, to be a nice target for beginners to see. Another target that I'm going to mention here, Cassiopeia, we have the double star cluster right about here. That's another interesting objects to look at. If you have a 25 mil eyepiece, you only get one, but if you do have a 2-inch eyepiece, you'll be able to see two. I discovered this quite accidentally when I was playing around with my 8-inch at Glen Lee. So if you're new, if you haven't seen it, please ask for it at the observatory night. Okay, and I can't really see it here, but that's what we see 20. That's a North American nebula, but I think I have it up here. Okay, so what I've done this time is I removed the atmosphere from it so you can see a little bit better. Again, this is tomorrow night. This is probably about 10:30. So some of the objects that we're able to see tomorrow night, we do have over here, like I say, C20 for the North American nebula. Of course, we have Hercules, and we have M13 right here and M92 right about here. Those are double star clusters. Again, if you're new, please have a chance to look at it at the observatory night. People there will be able to help you out. And of course, Saturn would be right up here, quite high in the sky. We don't have much of a core for the new for the Milky Way here, but it's still something there. Now, I have this at 2 a.m. This is where Mars is going to be just a few degrees of the moon here, as you can see here. Jupiter would be high, of course. Mars, actually, no, sorry, Mars. It's on another screen, actually, but Mars is right there, sorry. Mars there, we got Moon right here, we got Jupiter here. What's interesting here, again, we have the Orion constellation here, a winter constellation here, M42, another beginner's type of object to look at. Pleiades, I did try to take a shot at if they're in the star party there with my new tracking mount. I wish we had more time. At 5 o'clock in the morning, I was still raring to go, and I wish we kept on going. I was so dead tired trying to get home. So anyways, it was a really good night, that last night that we have. Okay, I do mention this, even though it's going to be a few days after we have the zodiacal lights, it's happening up to September the 15th. Even though I did say up to 5 o'clock, I did not see this, but if you haven't seen it, this happens in the morning. This is what it's supposed to look like. This was during the Arizona trip that I had here. It follows the path of the sun, so it's kind of like a pyramid effect, roughly the same brightness as the Milky Way. So again, that's in the early morning twilight. Now, like I mentioned before, we do have the partial lunar eclipse. This is a little diagram here. The magnitude of the sun on the sun, the moon, is going to just dip a little bit. So nothing really spectacular. I see here the magnitude is just going to drop a little bit, but it's on September the 17th for us, for Winnipeg. Again, nothing really spectacular. The moon's just going to just lose its little brightness. Now, there was talk about on the internet right now, the solar activity is going to increase, has increased already. So I always like to keep an eye on the number of sunspots that we have here. So last month, I know what's currently right now, but last month was 250. The month before that was 195. So again, it's on the rise. So again, this is the bell curve. This is the predicted values that we have for it. There's also another set of data. There's two set of data that we currently work with. But again, we're blowing the bell curve in terms of it. Now, I kind of put it closely to the weather here. CMEs, apparently there's two waves approaching the sun right now. CME, corona mass ejection. We do have one here, and then we have a second one here that's supposed to represent the sun, and this represents the earth. Now, actually, this kind of comes out a little bit better here. If you notice this here, it's kind of gray. See the intensity around here? It's going to be pretty intense. So almost blowing, like it's almost off the charts right as it approaches Earth. So that was stated last night. So again, we have two waves coming towards Earth, so expect some aurora activities happening. Now, what about the weather? Well, again, this is starting September the 12th. It's only 3 days. So again, it's going to get quite hot in the next few days, as you can see here. Now, for cloud, tomorrow it's going to be partly cloudy, but we are going to expect more rain. We do have some rain today, as you can tell, but Saturday night after midnight, we'll have some rain. But in terms of cloudiness, tomorrow night, it's going to be roughly partly cloudy, and it seems to be holding up quite nicely. So that's it. That's all I have for what's up for September 2024. Thank you.
Okay, now we have what's new with Danielle Pahud. You need your,
Yeah, sorry.
Thank you.
Thank you.
here's the mic. So just before Danielle begins, I'd just like to share with everybody that she told me when she said she would come this evening, that there was also something new with her, and that was that she got married a few weeks ago. So please join me in congratulating her.
Thank you. My husband Justin is at the back. We're trying to turn him into an astronomer. All right, so what's new? I only got one story and it's right in my wheelhouse. So I find this pretty exciting. So for those of you that don't know me, my name is Danielle Pahud. I'm an instructor in the Department of Physics and Astronomy. I am director of the Lockhart Planetarium and of the observatories. And my background is heliophysics. So. There we go. Okay. All right. So the news story I'm going to talk about today is that the Danielle K. Inouye Solar Telescope produces its very first magnetic field map of the solar corona. And that doesn't sound like a big deal for people that are used to seeing images of the corona. And we like to think that we can see the magnetic field in the corona because we see these beautiful arcades, but what we're actually seeing is the plasma. And we say, oh, well, the plasma just traces the magnetic field lines. And so we think we're seeing the magnetic field lines, but this is a measurement of the strength of the magnetic field in the corona for the very first time. And so I'm going to talk a little bit about the telescope first. Its very first light was in 2018. Its commissioning was in 2022. But this is a monster of a telescope. So this is the largest solar telescope in the world. It was built by the National Science Foundation with the National Science Observatory, national here being for the US. The primary mirror has a 4-meter diameter. It is situated on Haleakala on Maui in Hawaii. And its whole mission is to focus on understanding the sun's explosive behavior. And so we are, as Bryan said, reaching solar maximum. We are getting all sorts of coronal mass ejections. The sun is more dynamic and more active than it's been in decades. And so this telescope is really well timed. And it is capable of mapping the magnetic field in the corona. All right, so I may have actually shown this image before to What's New probably a couple of years ago, but this telescope, which they call the D-KIST, I'll call it I'll call it that. It has the spatial, temporal, spectral, and dynamic range needed to measure the basic magnetic structures at the solar surface and into the corona. We can observe the fundamental magnetic and plasma processes that are happening in the corona and near the surface of the sun. And it helps us to understand the role of magnetic fields and plasma in solar activity. And so one of the biggest problems in heliophysics is the coronal heating problem. So how do you go from a solar surface that is less than 6,000 Kelvin up to a corona that is 2 million Kelvin. So how do you heat something so fast while it's getting less dense and you're moving further away from the source of heat that is the nuclear fusion at the center of the sun? So how do you get it that hot? And so there's a big argument, and some people are like, it's magnetic waves, and some people are like, it's magnetic flares, but they're both magnetic. And we're not going to be able to answer that question until we can measure the magnetic field in the corona. And so this telescope has incredible resolution. And so this here is an image of the sun taken by the telescope, and we can zoom into a region here and a smaller region here, which we're going to zoom in. And here you can see they've highlighted this is a convection cell. So a convection cell is if water is boiling, you'll have water coming up in the middle, and then as it moves away from the heat source, it'll cool off and it'll fall back down. So if you're boiling a pot of water for pasta, you'll kind of get these columns or bubbles, and it's hottest at the middle and the center. And so there's some updrafts and some downdrafts. And the same thing is happening on the sun. And so these light, kind of broad, whitish structures are really hot plasma on the sun that's boiling up. And the darker, more amber colors over here is where the plasma on the surface of the sun is kind of cooling off and falling back down. The magnetic field is trapped in that motion, and so it's getting dragged along. And since it's getting pulled down kind of from two directions, we think that the magnetic field kind of gets bunched into these little carpets between the convection granules. And so these really bright kind of golden spots are regions of very strong magnetic field. And so here they highlight a convection cell that's about the size of Texas. And this little dot here is something that they're like, that's the size of Manhattan. And so they're, so, ever so US centric, the American telescope is, the thing that the Americans think is really big and the things that the Americans think is really compressed. But this is really incredible resolution on a solar telescope. And so what we can see has been really incredible, and it's given us all sorts of ideas about the dynamics right on the photosphere. And this is a few years ago. Okay, this I think should be a movie. There we go. So the first light for the telescope was in 2019. The telescope itself is a 4-meter off-axis reflecting telescope. You need a really large aperture, so aperture is the diameter of the primary mirror, to resolve the fundamental length scales in the atmosphere. And the fundamental length scale that this group is after is the photon scattering length. So how far can a photon go before it hits something? Which isn't that far at this level in the photosphere, so it's pretty impressive. They achieve a resolution down to 70 kilometers or 0.1 arcsecond in the photosphere, which again is quite something for a ground-based telescope. And they observe in the visible and also at 1.5 microns, so they focus on the infrared. In order to achieve this kind of resolution, they need adaptive optics. So they are actually actively beamforming this 4-meter mirror to kind of counteract the atmosphere. The dome is very open. You don't have to, so they really want, at this point, I mean, for any of you that have cleaned optics outside, I've made that mistake once. And if you happen to walk in front of the mirror, it gets really hot really fast. So if you have a 4-meter telescope that is gathering the light from the sun, it does not take long to get to like laser heat temperatures. And so cooling this is a marvel of engineering. And then you're also heating the air so much that you really want the ambient temperature to be as still as possible. You don't want this column of heat that is going to create turbulence in the atmosphere, because that's going to ruin your image. And so managing the temperature in this telescope is quite the engineering job. Yeah, so they've also have large format infrared cameras for this. So quite the instrument.
That infrared,
Sorry?
that movie infrared.
Yeah, I think that one's part infrared. Okay, so here I went down a bit of a rabbit hole for technology. So they have heat dissipation technology at the prime focus. They have adaptive optics. So they have a deformable mirror that has 1,600 pistons on the back to change its shape 2,000 times a second. There are beam splitters and filters that allow 5 cameras to record simultaneously. So this is a little video that shows you the optical path. So the light comes in, it hits the primary mirror. It's a secondary mirror. The secondary mirror is where all the cooling happens. They kind of bend it back a few times, and then it goes straight down into this separate room, which is called the gAIL laboratory, which is on a rotating slab that is separate from the rest of the building, so they can stay very stable. It comes down, and then it hits a bunch of beam splitters so that the light at different wavelengths can go into the different appropriate instruments. But what that means is that they're taking the same light and they can take 5 images with 5 different instruments roughly at once. So the amount of data they can gather is incredible. It's terabytes a day. So really neat design, powerhouse of a solar telescope. Oh, this is okay. So this is the light path here. This is the 4-meter mirror. Okay. Here are some images that blew my mind a little bit. So that is up here, the back of the telescope. This is the primary mirror. And this is one of the optics table with all of their beam splitters in the gAIL laboratory. So there are a bunch of instruments. You'll notice that taking the spectra and polarizing things is very popular. So they have a visible spectropolarimeter. here. So this image is in the visible for optical wavelengths. The spectra means that it is splitting up the wavelengths into small chunks. And the polarimeter means that it's looking at the orientation of the electric field of that light that's coming in. They have a visible broadband imager, so they're looking at a lot of light there, and they have a wide field camera here. They have a visible tunable filter, which is an image spectropolarimeter. So here they take a whole image, and then as they take images, they scan through wavelengths. So I think this one, there's a slit, and this one there's not, so they can see a much larger region. Then they have a diffraction limited near infrared spectropolarimeter. So another spectropolarimeter, but now they're looking at the near infrared. And here they have the cryogenic near infrared spectropolarimeter. So you can see that they have a lot of instruments that do similar things, but in slightly different ways. So they really want to be able to get all of this information. And the reason they care so much about getting accurate spectra is that the corona and the sun have a huge range of temperatures that has both broadband emission, Doppler shift. So as things are flowing in and out, those wavelengths, even if they're being emitted at specific wavelength bands, are going to be shifting around. And then the thing they really care about, the magnetic field, causes a very subtle effect called Zeeman splitting, where the spectral line splits, and the amount that it splits corresponds to the strength of the magnetic field. And so they are looking for a spectral line to split a little bit, and that gives them the strength of the magnetic field in that direction. Okay, so here are just some more jaw-dropping images from the telescope. So I apologize that I don't have the scale on here, but this is a sunspot with a penumbra. Here we're looking more at the chromosphere, but we're looking at another sunspot. You can just see all of the little filamentary structure. And here we have something that was new to me, but these are called pores. And this is kind of the beginning of a sunspot. And so it's regions of strong magnetic field, but not strong enough to have a penumbra. But you can see all of the filament here. It almost looks like hair, which is just incredible. Okay. So that's all about the telescope and some of the images, but the showstopper is the measurement of the magnetic field in the corona itself. So here in the pinkish purple, we have an image of a coronal loop that's fairly small on the limb of the sun. And then here we have the measurement of the magnetic field. I've got some nicer images of that in a little bit. But why do we care? Why is this a big deal? For decades, astronomers have been looking at the strength of the magnetic field on the solar surface. And then we use physics models, assuming that the magnetic field is the strongest force around, to kind of generate magnetic field models, what we think the magnetic field is doing, close to the sun and further out. And then we use that to kind of guess how the magnetic field is going to behave. So this here is an image of the sun today from the Solar Dynamics Observatory, taken by their HMI instrument, which is the heliographic magnetogram imager. And so in black is one polarity of magnetic field, in white is the other. And so you have regions of strong magnetic fields. You can compare this to an image of the sunspots, and the sunspots are usually in these regions of either very black or very white. This is another SDO image from their AIA instrument at 193 angstroms. And you can see, so this is more coronal plasma, that's quite a bit hotter. But you can see that these regions of very bright plasma correspond quite well with the regions of strong magnetic field. And interestingly here, you have some strong magnetic field on two edges, right along the edge of a coronal hole. But this all is the magnetic field right on the surface of the sun. And for the most part, we can only see the sun one side at a time. And so if we're looking for space weather, the global geometry of the magnetic field actually plays a really large role in whether or not a CME gets deflected on its way here, or whether we're going to be blasted with some fast solar wind or some slow solar wind. And so a lot happens between the surface of the sun and about 30 times that solar radius. And right now we just take measurements at the surface of the sun and kind of make some big assumptions and then make a model for what we think the solar wind is going to do further out. And then we compare our models with images of the corona and we're like, did we get it right? But we don't really have any measurements of the magnetic field in the corona. This is, so when we want to simulate the global magnetic field, it gets even worse. Because we can only see half of the sun at the time, and the sun rotates once a month, we have to wait 2 weeks to see the other half of the sun. And as anybody that's been watching sunspots recently, the sun is changing. So it's not even the same sun by the time that first round comes all the way back around. And so for my thesis, what I had to do is I had to build global models of the corona to put into my solar wind model. But you need the whole sun to make a global corona, which means that you need a magnetogram with, so this on the x-axis is latitude, so you kind of go from 0 to 360. So this is today, right? So this is the sun today, and this is the sun a month ago, but this was in front of the sun 2 weeks ago. And so now you need to make this a full map, but this is 2 weeks old, and you need to somehow merge it to this, which was the same sunspot, but now it's evolved. You'll notice that the poles are really smooth because we measure line of sight magnetic field, so the magnetic field is coming out at you. So we have really good measurements in the equatorial region, but bad measurements at the North Pole. So you somehow have to make a nice magnetic field out of this mess, which is, isn't really accurate. And so this is what space weather predictors do. And so they take the magnetic field on the surface of the sun, and then we say, okay, I'm going to assume that the magnetic field is the strongest thing there. I'm going to assume that there aren't any forces. And so my magnetic field is going to arrange itself into like the lowest possible energy configuration. What does it give me? And so we make what's called a potential field source surface model. And so this is 2 examples from Predictive Sciences, Inc., which is a group that does heliophysics. And so this is an example from solar minimum, and it kind of looks how we should expect it to look. We have closed magnetic field lines here. So we're expecting kind of a wispy eclipse shape, closed, slow solar wind at low latitudes, and you have the nice open magnetic field lines at the poles. So that's a nicely behaved solar minimum case. And the solar maximum, we know that the magnetic field is a lot wackier, there's a lot more activity, and so we have a much more chaotic magnetic field. And so we put those into our solar wind models, and then we run our solar wind models, and then we have our spacecraft in front of Earth, and we say, did we get it right? And we compare the solar wind actually with what we predicted. And all things considered, they do a pretty good job, but it's definitely not perfect. One of the other things we can do, and one of the things that predictive science does, is every year, whenever there's a solar eclipse, they're like, can we predict it? And so here is an actual image of the solar eclipse from this is 2017, I think. It's not this year's. I was trying to find.
That's 2017.
It's 2017. Yeah, it's Oregon, right? So I was trying to find their version of this plot for the last eclipse, and I couldn't find it yet. But so this is what was actually there. So you can see kind of a solar minimum corona shape. So you've got these wisps that are closed, and then you have these nice tendrils that show open magnetic field line. Based on the photospheric magnetic field, which is shown along this disk as red and blue, they model the magnetic field line, and you can see that we're expecting some larger arcades here and here, which match these pretty well. And you can see that there's a bit of a spindle here, but it's probably not as prominent as this. So these are the images. And this is what they predict based on the measurement of the magnetic field line. And so you can see that it's close, right? This is pretty good, this is pretty good. They don't really have this, but overall the shape is pretty close. But this, up until we can measure the magnetic field here, is the state of the art. And so now, with this new, okay, so that's the global magnetic field. If we want the magnetic field much closer, we apply more models here. We can measure the motion of the surface of the sun. So maybe I'll explain this plot a little better. So what I have in grayscale is a measurement of the strength of the magnetic field. The colored lines are simulations of where we think the magnetic field lines are doing. So in green, we have these arcades, which are kind of static. So they would be kind of like these lines here. And in red are flux tubes that are twisting that we think might flare. And so you can kind of see this S shape. And so astronomers think that you kind of get this S shape, and that represents a twist that's about to make the magnetic bundle unstable. Magnetic field lines don't like to be twisted. And so we think that might be a precursor to eruption. And so we can use physics models like magnetohydrodynamics, and we can watch movies of this erupting and then use the photosphere to measure things, put in a model, see what the model does, and then try and recreate our observations. But we don't have measurements of the actual magnetic field here until now. So now the DKIS telescope has unprecedented maps of polarized spectra at 1074 nanometers, which is emitted by an iron ion. So this is a specific atom in the corona. We can measure the Zeeman effect, which will give us the magnetic field. So here we have an SDO image of the solar limb. So this is the solar limb here, and you can see the magnetic field arcades, or the plasma arcades that we think is tracing the magnetic field. And here we have the DKIS telescope measurement of the magnetic field. And so here we have the intensity of that field line. Here we have the circular polarization of that line, which tells us about the magnetic field. And here we've matched it with the magnetogram. And so here we have magnetic field strength simulations. And so this has sort of opened a whole new, I was going to say kettle of fish, and I think I'm mixing my metaphors. But it's opened a whole new range of opportunities for the kind of science we can do on the sun. Right, that's everything. Thanks. Yeah, Michelle.
The new technology went from temperature increases.
Okay, so the question was, do we think that the new technology might help explain the temperature increase as we go out? Yes, I do. So I think this is the very first image of the magnetic field strength. I think they're working towards getting a vector measurement, meaning not only the strength of the magnetic field, but also the direction. And they can take, I think in one of these images every second. So I think once they get it, once it becomes like a well-oiled machine, I think we'll be able to have movies of the magnetic field. And then we're really going to be able to start to see the dynamics of the magnetic field strength at this point. And I think that's going to allow us to sort of differentiate between the wave and turbulence driven heating and some of the flare reconnection driven heating. So I think it's going to help us answer some of those questions. I think it's also really well timed with the Parker Space Probe and the ESA solar orbiter. Like we have in situ measurements that are getting closer to the sun. So I think kind of with that multi-pronged approach, I think we're well poised to make some great advances. Yeah.
I have two questions. You just answered the one about Parker Solar Probe. So the other question I have, can you explain the Zeeman effect? Like, how does that work?
Okay, great. I'll be honest with you, there was a point in graduate school where I was like, yeah, on it, and now it's a little fuzzy in the background. So I think, so what happens is, as the light is being emitted from the, so like when we look at a line like this, we're looking at a transition of electrons from one region to the next. As an electron orbits around a proton, the orbit itself is creating a current. So ionized atoms are themselves little magnetic dipoles. And so that energy transition is going to be slightly easier if the magnetic dipole is aligned with the magnetic field as opposed to against it or perpendicular to it. And so there is a tiny little amount of energy difference in how that transition happens because there's an external magnetic field. And so that tiny energy difference means that the wavelength of the photon that's emitted in that transition is slightly different. And so now that now, like if you have enough light, which now we have a 4-meter telescope, so we do, and you have a sensitive enough spectrometer, you can start to see, instead of one peak for that transition, you can see a peak and then a little dip and then another peak. And the width between those peaks tells you what the magnetic field strength. Yeah.
Thank you.
Yeah.
Were they using iron 12 because it's dense and also highly charged? Is that?
They are using, I think, so the question is, are they using iron 12 because it's dense and highly charged? I think they're using iron 12 because it's not dense. Because if it was really dense, then you would see it everywhere. And I think you want to be able to pick out a fairly narrow feature. So, but it is highly charged, and it's probably well away from other emission lines. So, yeah.
Just a comment, when you were showing the polarization of the corona from 2017, that was one of the first, not maybe the first eclipse that we watched. We had cross polarizing filters. One was going this way and one was going this way. And we observed that one of those plumes disappeared.
Oh,
When we
cool.
went back and forth, came back, went back, you know.
Oh, that's neat.
Very cool, like, kind of surprised me. I didn't know anything about that, so I'm really interested in that slide.
Yeah, that is really neat. Cool. All right, thank you.
Okay, now we'll break for about, it's 8:25, maybe about 20 minutes, 25 minutes. And reconvene at 10 to 9. Is that too long? Too long? Oh, 10 minutes. All right, 10 minutes. Ed's a taskmaster. 25 to 9. Is there a place to get coffee? No place to get coffee yet. Okay, so that might be why. Anyway, chat for 10 minutes. People on Zoom, chat for 10 minutes, and we'll reconvene in 10. Sorry to put you on the spot.
Put me under the bus, yeah.
Sorry.
No, it doesn't really matter.
It's interesting.
Yeah, very interesting.
Yeah.
It was good. I'll have to give her one drive back.
This guy.
Yeah.
No one just did it. Oh,
I think.
Let's see if we can make sure my videos are gonna work.
okay. So you want to take it off sharing?
Let me just see where we are.
So want to keep that menu out of sight during. We have to get everybody.
Okay, while you're on.
So just while we're waiting for Jay to start, there were some lapel pins produced for this year's Spruce Wood Star Party. They're dated 2024 and they show kind of cool image of the telescope between trees and a big bright star up above. And this sort of going to be a collector's item, we hope, for us at least, because there'll be a new one next year. And there are some left over if you'd like to purchase one of these, or we'd like to collect donations toward the Telescopes for Kids program. And Damon has a bag of them if you want to give him whatever donation. We only need one more person to come forward about winning All-Star Telescope gift certificate. We've got 6 now total. And I heard from the person who told us that the 18th was a Bomber game, that it's actually okay. The 18th will be the next meeting. The 11th is the Bomber game, which is why I moved it in the first place. Okay. So now our main speaker is somebody that I know really well, and many of you know him. Jay Anderson has been a RASC member for 50 some odd years or so.
Close.
And has done a lot of talks in the past. And this talk he prepared for Spruce Woods a couple of weeks ago. So he's going to modify, I'm not sure. This is to substitute for Mike Caracas's planned talk. So what we're doing is we're swapping Jay's talk, which was planned for November, and I'm hoping that Mike will be available for our November meeting. Okay? Thank you very much, Jay, for stepping in at very short notice.
We were actually 3 blocks away from home. Had to turn around and go back and get this thing. Now, I read somewhere that if I hit the Alt key on this, something will happen to this. Hello. So there it is. Hit the Alt key and that little menu will disappear. Okay, this is I've forgotten when I took this, sometime within the last year, and it demonstrates one of the things about Aurora, several things actually, that we'll go into in the course of the next 40 minutes or so, is that, first of all, it can be quite an explosive event. And you can go from looking at nice curtains off toward the north, and all of a sudden your whole sky is full of this greenish color. The other thing about it is that very short exposures, which you can do with a bright aurora, make for much more interesting movies than ones that are fairly long. By short, I mean 2 or 3 second exposures taken continuously, as opposed to 5 or 8 second exposures, because you get a much more smoother motion to your auroral videos. So I'm going to look at the past at the start. We're going to talk about what the sun has to do with this process. We get into it later. I'll talk about photographing an aurora somewhat. And I'm going to talk about some of the legends that have come up about auroras over the past years. You have to think about it that not everybody sees an aurora. If you're part of the Inca Empire in South America, you probably have no familiarity with the aurora at all. And even the Greeks, it was a very, very occasional thing for them. So you're really going into northern communities, northern hemisphere communities, to work out auroral legends. We'll go and talk about that a little later. So it came from Galileo, which seems rather late in history, that something that was at least known to earlier civilizations, and especially as the Romans spread northward into Germany and There were the various hordes that came out of the northeast that attacked the Roman and Greek empires, that there was certainly, it was more than just a once in a lifetime event. And probably when the sun was at a maximum, they might, from our current experience, get maybe 2 or 3 events a year that would be seen as far south as Greece. But nevertheless, it was Galileo, and he borrowed from both Greek and Roman names. So he's got Boreas, which is the north wind, and for Aurora, which is the goddess of the dawn, because Aurora was equated with, looked like the dawn to the Greeks. And they knew that on the very short days of summer that it was a little bit bright toward the north if you went far enough north. And just as an aside, this wonderful picture showing Aurora rising, coming in her chariot and bringing the sun was actually done with an AI program where I said, draw me a picture of a goddess riding a chariot at dawn, and this is what it came up with. So, you know, I'm now a master of the AI world. To tell you the truth, I had to do it 3 times before I got one I liked. The Babylonians knew about it. Now, Babylon really didn't go much further north than, say, present-day Israel. And most of that was the Akkadian Empire, which took over Babylon later on. But they already had these things. And what you see here is from 567 BCE. And all those funny characters in the middle are the sort of modern literary translation of what's written on this tablet, or part of what's written on this tablet. But this is the sort of way they take the characters in cuneiform and translate them into alphanumeric characters, and then from that they can translate them. And what it says is what you see on the screen, a red glow in the west. But we know that from our own experience that when you get a really, really strong auroral event, it turns the sky red. And quite often that reddish color is visible in North Dakota, but when you look aloft over top of us, it's green. So in a sense, an aurora that goes a long way to the south, you sort of expect it's going to have a reddish color. And that's the reason for associating that sort of kind of maybe the description that was in the Babylonian text with the aurora. And the red is diagnostic. Here are a couple more of them, a little bit longer translations. And here you can see drawings of the actual cuneiform characteristics, which is a common way of doing this, because I talked to a fellow once who could read cuneiform, a fellow named John Steele. If you ever go into Babylonian literature, he's quite prominent in the field. And he said that he couldn't read the tablets unless he held them in his hand, because the characters are so subtle, and they're clay tablets that you have to keep turning them in the light to catch the characters, which are sometimes very shallow. And so what happens is that people will do these many, many tens of thousands of these tablets and draw them so that they're easier for others to interpret. So you can see through letters 1 through 6 is a translation, what's on the left side, and then on the reverse side, it tells you who wrote it. And in the second example there, there's a shorter passage, but now we have the name of the person that wrote it. And having names of people in the cuneiform tablets, the scribes that write these, is a little bit unusual. Now, Babylonians watched the sky every night and kept diaries about what was happening. And so they would measure when the moon went past certain stars and so on and so forth, and whether there was thunder or lightning, and what the price of grain was that day in the marketplace. And so because they were tasked with the job of keeping track of the sky, any aurora they did see usually got recorded. It's just that we don't have a complete set of tablets over the 1100 years of cuneiform writing. We get up into the 1100s. 900, 1200s. Auroras were treated more scientifically and yet no more scientifically than they had been in the very earliest times. Reflected firelight. Well, that's okay if you think that the world is flat and over the edge of the world there's some kind of perpetual fire. And what you're seeing in the aurora is the reflection of that fire. But the Greeks were certainly aware of ice crystals in the ice crystal formations that we get around the sun sometimes. And I thought that way light was reflected from those. So they were putting a little bit more of a scientific approach to it. When you look at these pictures, you wonder if they actually saw an aurora. It's almost like these pictures came from somebody else's description. You can see the red sky here on the left and maybe some streamers, but it's the kind of thing sometimes when you look at these medieval reports, you think, you know, they're actually looking at it when they did this. But nevertheless, you can see that the consternation, I guess, and certainly the attention that people on the ground are paying toward these sorts of things. We see them so often here that we don't realize how amazing they are to other people, unless you are on some kind of a message board, or in our case, it's for solar eclipses, and people talk about seeing aurora, or if you go into something associated with spaceweather.com, once you get south of North Dakota, seeing an aurora is quite an event. Whereas here, it's kind of, oh, well, just another aurora. So we've already had a little discussion of the sun's magnetic field. And if you look in the top left corner here, you see a sort of what the sun's magnetic field looks like from a large distance. And it looks just like the Earth's does. It's a bar magnet, the kind of thing you played with in school where you put a magnet under a sheet of paper and scattered iron filings on it, and it traced out the magnetic lines that came out of the North Pole and went into the south, and actually the other way. And when you look at here on the right-hand side, the big image, you see the global magnetic field of the sun, but at a much, much closer and higher level of detail. And you can see how magnetic field lines seem to come out of sunspots and disappear into what might be sunspots. And then it's kind of like a hairball if you own a cat. And so each one of those lines represent magnetic fields. And so it's not a large, even magnetic field, except at a very large distance. In detail, it's a whole bunch of places of magnetic activity with magnetic fields coming out of the sun and disappearing back into the sun. And some of those places are where there are sunspots, which you can sort of see in that gray image, the blacker spots. But there are other places where there's no sunspot. And when you get down into real big detail in the lower left there, you can see how the magnetic field lines are being traced out. This will be an image in an iron wavelength, a very, very narrow wavelength. And you can see how the atoms that are giving off this light are trapped in the magnetic field, and they trace out the shape of that magnetic field. This one is a pretty quiet one. It's just a nice loop, and it's probably going to last there for several days or weeks and then gradually collapse. But Danielle has pointed out these magnetic fields can get quite twisted up because the sun's surface is moving, it's churning, it's always boiling. And so these things get drawn together or drawn apart. Magnetic field lines run close to each other and suddenly decide to snap together or release large amounts of energy. A fellow named Miloslav Druckmuller is famous for his images of solar eclipses and coronas, and you've probably seen them several times. But he also works on some of the observations of the sun's surface from the satellites. And there are two things about his images. They're unprecedented detail for almost any scientific image. The technique he uses to reveal the solar corona, like no one else can, he also uses to reveal the structures inside the sun. And so it's well worth going to his webpage and just looking at these marvelous images that he takes. He's a professor of, well, essentially image processing. And to see this structure you see here, which is the eruption of a filament coming off of the surface of the sun toward the lower left, this is what we call a coronal mass ejection. It's basically some kind of energetic event on the surface of the sun that has thrown a large mass of material out into space, and that material follows or carries with it the magnetic field that it had when it was on the surface of the sun. So it's not only throwing material out, it's throwing out bits of magnetic force or field. And so here you can see one here. This is an eruption. Notice how much of this falls back, but not all of it. And that amount that keeps going is shot off into the solar system, escapes from the sun. And because the sun is rotating, this material, which is flowing off continuously, this is an eruption, but there are also some parts of it that are flowing off continuously. They carry the magnetic field, so it's like going out into space, but because the sun is turning, it's a little bit like a water sprinkler. So these things actually form spirals around the sun because the sun rotates in a 29-day period. It's quite marvelous to watch these things, the many of them. And when we see these things with one of our hydrogen alpha telescopes, we only see a piece of them at an instant of time. Only if you watch for a fairly long period of time or do some photography over a course of a day do you get to see these things moving the way this image is doing. There's also something that was alluded to, is this big black area, which is rotating off to the right in here, is what's called a coronal hole. Now, you'll notice in my maps of the sun's magnetic field, the magnetic field lines turn back down to curve back and rejoin the general magnetic field at the surface. But there are places where the magnetic field simply goes out into space and doesn't turn back into the solar surface, except along the edges. And these are what they form, these dark areas on the sun. If you look at the sun in a particular wavelength of the light, this will be probably an X-ray or an ultraviolet image here. And that black area is a coronal hole, and stuff just flows out of these holes. It doesn't need necessarily an eruption, but when an eruption does occur in a coronal hole, then you get a really huge amount of material being thrown off. So it's like there's a continuous rain of material flowing away, and then there are periodic eruptions that throw much more material. And that has quite a bearing on what happens at the surface of the Earth. In fact, what comes out of coronal holes is by far and away the largest part of the flow of material from the sun that comes toward the Earth. Now I'm going to see, this is a satellite view of the flow, and you can see there are sudden parts of it that become much more intense, and that would be an eruption from a coronal mass ejection inside a coronal hole. So in generally, there's this low level flow like this one here coming out from the sun within periodic enhancements, which we would see as a solar storm like the one that hit the Earth last night, which I've got to say, in spite of the appearances of spaceweather.com, it was really a bit of a dud for us, although I think it was pretty spectacular over Europe. So we take a look at these models, and here you can see the general spiral form of the magnetic field coming out from the sun, and then this coronal mass ejection, which doesn't, because it's an instantaneous event, it doesn't have that spiral structure to it. But you notice how it sweeps up material ahead of it. Now the Earth in here is about halfway out on the right-hand side from the sun at the center. So when these CMEs, coronal mass ejections, come past the Earth, they carry with two things: a lot more material and a much stronger magnetic field force from the sun. So there's two things that take away here. One is there's a continuous rain of stuff from the sun. So the Earth's magnetic field, which traps some of this, is always being continuously replenished. And secondly, there are instances when you get a lot more of it. It's like somebody holding the hose with a bend in it and then letting it go while you're looking at it in the wrong place. So here's what our magnetic field looks like. You can see that the side on the left, which is facing toward the sun, has actually got a fairly nice circular structure to it. This is on a quiet day. There's no big impulse coming from the sun. And because of the force of this material flowing away from the sun, it pushes the anti-sun direction, a tail of material way, way back, streaming. In fact, there are parts of this that can reach as far as Mars, although it's quite a little fairly tenuous when you get out there. So the magnetic field of the Earth has got an enormously long structure, and that area where the writing is filled full of this material that's coming from the sun. And some of it comes in along the edges, leaks in just as the flow past this area, and just gradually leaks into the Earth's magnetic field. So it's continuously being filled up with a low level flow of ions, mostly electrons from the sun, but also atoms that are ionized as well. And so that whole area where the printing is filled up full of material, but it's quite benign. It's quite happy to stay there. But at some point, it gets too much. These magnetic fields are each going in opposite directions. You remember that there's a South Pole and a North Pole. So if you look at the left-hand side, you can sort of say, well, it comes out of the north side and goes in the south side. And so the directions are opposite. One is going to the upper left, and the other one is coming in from the lower right. And it's the same in the flow and the tail. The magnetic fields are in the opposite direction. They're similar directions, and they can connect to each other and at some point in the middle. And we'll have a look at what happens in that. So here we have a better diagram of it. The plasma sheet, as we call it, is the area on both sides of the sun. We have the Earth's magnetic field has this little cusp. You can see where they've written the words, well, polar cusp down there in the bottom. The Earth is tilted toward the sun. And in the course of our orbit, we have one time when the cusp is pointed toward the sun, and another season when the cusp is pointed away from the sun. And those periods are actually on the solstice, and the equinox rather. And this is the season we're coming up to. It means that the flow of the solar wind can get into that cusp a little more easily. So we actually, around this time of year, tend to get stronger auroras than at other times of the year. And on top of that, we have a solar cycle which is climbing to a peak. And at a third event, the best aurora come in the 2 to 3 years following the peak of solar activity. So we're actually entering into a much greater period, a period of much greater solar activity over the next couple of years. And we should be looking for some pretty spectacular auroras, particularly like winter nights that are clear. They're a little hard to tolerate, but the skies are marvelous when the aurora is going. So we have all these particles stored, and you can imagine that the bottle, the magnetic bottle, this plasma sheet, is pretty much full. So when you get these eruptions from the sun, it's like overflowing the bottle. And the first thing that happens is Generally, this long tail of the plasma sheet tends to collapse and pinch in a little bit. Particles that are in that plasma sheet are ejected both away from the Earth and toward the Earth as these magnetic field lines connect with each other. They release all of the energy they've been carrying. And so somewhere out toward the orbit of Mars, there's a big blast of solar ions that go out. But what we like is that they come in toward the Earth as well. And they follow these magnetic field lines, which you'll notice tend to come in toward the North Pole and toward the South Pole. So those ions, when this energy is released or when the plasma bottle is filled, are the ones that interact with the upper atmosphere, collide with molecules in that atmosphere, and give us our auroras. When you look at that in a sort of three-dimensional shape, you can see why it is the magnetic field focuses down in the poles in what we call the auroral oval, which is a circle around the poles where these magnetic fields dip in most closely to the Earth, where they're most likely to interact with the atmosphere. Because if you're out toward the equator, the Van Allen radiation belts, which are holding all of these particles in the ionosphere, tends not to be in a magnetic environment where these ions are going to be dumped down into the atmosphere. And these ions are actually going back and forth very quickly over a period of fraction of a second between the North Pole and the South Pole. They're just oscillating back and forth. They have an electric field because they're electrons, and so they're trapped in our magnetic field, just the way as the stuff flowing from the sun is trapped and carrying the sun's magnetic field. And so we get this little area around the poles where the magnetic field comes closest into the atmosphere. And the same is true on the South Pole, but there's not really very much land close to the southern auroral oval. So aurora are much rarer. Reports of aurora are much rarer in the southern hemisphere than in the north, because the farthest south that you go in the southern hemisphere is only about 40 degrees south, whereas you're barely starting North America at 40 degrees north. Well, the important part of it is just starting there. So you get this little band around the North Geomagnetic Pole. And curiously, you'll hear stories in the newspaper that the Earth's magnetic pole is wandering to the north, and one of these days it's going to be in Russia. Well, that is true, but the auroral oval is not around the North Magnetic Pole. It's around what's called the North Geomagnetic Pole, which is a different kettle of fish, to borrow something already used in this meeting. The geomagnetic pole is not moving very quickly, and it's actually very close to Ellesmere Island. It's going to remain there for some time. And this is important to us because look at where Winnipeg is. Winnipeg is very close to the most southerly extent of the auroral oval. Edmonton is also close to the auroral oval, but farther north than we are. And of course, you can look at Whitehorse and Yellowknife and over in Europe, various places in Finland. We actually get our auroras because of this favorable orientation of the North Geomagnetic Pole. And eventually that pole will drift off, but I think we have hundreds or maybe even thousands of years before Winnipeg stops being one of the go-to places for aurora. Our industries have never taken advantage of this. The Swedes and the Finns and Norwegians and also Alaska and Yellowknife make a big deal out about the going to see the aurora. But in fact, you would be pretty close to underneath the average position of the North Geomagnetic Pole if you went to Thompson. Well, we all, most of us anyway, use spaceweather.com to find out whether or not we're going to get an aurora. So they produce these maps, and here are two of them. One with a moderate level of auroral activity. You see the yellow in it. I hope you can see the yellow in it. Well, not quite so prominent here, but that yellow in it is well, you can see it's a probability of aurora. It's not a guarantee of aurora. When you see yellow, it doesn't mean it's a moderately strong aurora. It means you got more than a 50% chance of seeing an aurora. But in fact, the higher the probability, so when you get into the reds, like last night, very big area of red last night, your probability of seeing an aurora gets very close to 100%. And there was an aurora last night. I saw a few small photographs of it, but we were confounded by cloud and smoke. So from my point of view, which was from Glenlee, I went there because it was better weather down in Glenlee. It was a dud. Nothing happened. But over Europe, they got a pretty good aurora. And when you see the great big areas of red, you start thinking about aurora that's going to go down into South Dakota, and they'll get the red skies that go along with it. So here's what happens when a solar storm hits us. Here we are, just a quiet little day. You can see the magnetic field sort of fluctuating a little bit. And then this guy comes in and blows it all back, really compresses the part that's facing the sun on the left and stretching out the back end of it. But that back end gets squeezed together. Those magnetic field lines reconnect, and the ionosphere and the plasma sheet are filled up full of material, which then crashes into the Earth's atmosphere. So it's quite an involved process, beautifully modeled here. And of course, this is exactly what we look for and why we pay attention to spaceweather.com, which tells us these things are coming. And just reading today about somebody who does the weather forecasting for space weather, which a number of agencies usually associated with the U.S. military. I visited one of their forecast sites in Australia, so there's a combination of Australian and American forecasters, and there are Canadian forecasters. And anyway, they said that their forecast accuracy was far worse than my forecast accuracy. And for those of you who don't know, I'm a weather forecaster. So I also had a friend of mine who was, well, basically did forecasting for financial forecasting. So you could call him an economist, I guess. He said he was in the only business that had a worse forecast record than I did. But I think he didn't get into space weather forecasting, because certainly last night's forecast of heavy activity didn't pan out very well, at least for us. Okay, types of aurora. Well, you can go to numerous web pages and find a lot of different kinds, but this works out pretty well for me. These pictures are all taken locally. So you get the arc, which is just a green band up toward the north. You get these curtains. We always kind of wait for the arc to turn into the curtains. The curtains are beautiful, but the curtains that we see are curtains that we see off to the north, because the north is normally where the auroral oval is. So if you don't have too much activity, you're going to be looking at the curtains off toward the north, so you see them from the side. And the best way to see curtains is actually underneath them. And this picture on the upper right is photographed from Norway, where we were closer to being directly under the auroral oval. So this picture on the upper left might actually have some curtains in it, but they're all smushed out in the distance. Whereas when you look at this one on the upper right, that's what they look like when you're under it. That's what you would see on a day when we had a good aurora. If you went to Thompson, you would be seeing those curtains up above you or close to above you instead of off in the distance. And the bands is another form, and these rays, that was a spectacular night that night. And that picture is from Beaudry Park. So you don't have to go very far on a good night with aurora. Just got to get out of the city to someplace that's a little bit darker. The corona is sort of what we were expecting last night. That's the big eruptions. Those are days when the whole sky fills with aurora. And you can see this color that you see here is typical of what you might find over Winnipeg. This would be photographed from up near Birds Hill Park, maybe, although there's so many people up there now, it's not a good place to go to. Could be Oak Hammock Marsh, which is not too bad if you don't go into the marsh itself, but go a little north of it. So these coronas are signs of a major eruption, and they're the ones where the folks in North Dakota and South Dakota are going to see a red aurora. But I have seen completely red auroras here, so it's not a guarantee, but typically the red auroras you see in photographs are from people a little farther south. And I actually find these coronas, they're interesting up to a point, especially because they're pulsing and changing at 3-second intervals the whole time. But after a while, I get tired of them because they don't have nice curtains. But that's personal opinion. I really like the curtains. And then there's other kinds of auroras, like this red patch that just hung in the sky there for the longest time. And then there's the one called Steve, which we'll cover a little bit later. So when do you want to watch for the aurora? When it's really good, I like to get out really early before it's dark. Because if the auroral oval is forecast to be up in the 80 to 90% range, so it's showing red tinges or even deep red, you know that it's probably going to be a corona. But before the corona starts, usually the northern sky early in the evening dances with all kinds of spikes and curtains. And so you get the really moving dynamic. And then you get the totally different kind when the corona develops, which if you're going out in the winter, say at 8 o'clock, by 9:30, you might have the corona over top of you. So that would represent where just underneath the words auroral oval, you see a relatively straightforward one. And then as you turn into more darkness, you get into the much more active twisting and turning of the aurora or the corona, if you're going to have one that night. And then as you go around to the early morning, it becomes patchier and sort of loses its intensity. So there are actually phases through the night. Now, the primary time for aurora is around midnight on standard time. So that would be 1 a.m. in the morning right now. So you should never go to an aurora, plan on quitting before 1 a.m. if the skies are decent. But if you're going to have a good one, you can still get a really nice show at the start of the evening. When you look at these things from a satellite, you can see that you can have a really active night and get a really lousy aurora. If you're sort of in one of these little gaps, like north of Edmonton here, that big bright spot, that's Edmonton, Red Deer, and Calgary, those 3 bright spots. If you're looking off toward the northwest, you'll see a piece of good aurora and maybe a not bad one off to the northeast. But looking straight north, you're looking into a hole. But these things are moving all the time. So don't give up because your aurora looks kind of so-so in the night, because these things are moving along, and all of a sudden you may find, usually after you put your camera away and folded up the tripod, the sky suddenly erupts. Yeah, I know one night I was doing that. It was a nice aurora. I decided I'd had enough at 1 in the morning. I bent down to unplug my battery from the cameras, and all of a sudden I realized my shadow was on the ground. And I looked up. In that 10 seconds, the whole sky went from a kind of a nice aurora to the whole sky being full of green. And that's how these storms can come on extremely suddenly. So typically at sunset, you see this sort of thing. And if you've got this much light and you're seeing this, you know you're in for a good night. If you have to wait before it's dark before you start to see this green band up north, it may not be the greatest of nights. These purple spikes are very interesting because they're common when in the early stages of an aurora, usually not too long after sunset. And these are not caused by electrons flowing in from the sun. These purple spikes are actually sunlight reflecting off of the ions and interacting with those ions and glowing in purple colors. So you will only see them when there is sunlight illuminating the top of the auroral column. And that's why you see them in the evening and presumably also in the morning. And they will fade away as that part of the atmosphere gradually moves into darkness and be replaced with either green spikes, or the aurora will continue to develop farther south. So the purple spikes are kind of a little different process going on. I should point out right now, though I'll cover it later, these are what you see in a camera. You can see the purple color, and you certainly see the spikes, but that low light level means that your eye tends to see them in shades of gray instead of these colors, unless they're very bright. Later on, your little band around the south will start to expand upward. We see these over at Spruce Woods fairly often. And we had one night with a little bit of an aurora that stayed down low on the north horizon. It didn't expand to this extent. But when this is starting to happen, sort of all bets are off. Are you going to get into a major storm, or are you just going to keep these dancing curtains off toward the north? And the arch itself is not particularly interesting, although parts of it, like the right-hand side here, might be pretty good and worth watching. Oops, went a little too fast there. So I talked earlier about taking exposures quickly. Now here we are in the evening, so we got a lot of purple colors in it, and it jumps around a little bit. But it was bright enough, I was able to take very short exposures on this, probably of the order of 2 seconds each. So it puts together a very nice and smooth aurora. And it's up to you whether you like this sort of dancing colors in the sky or whether you prefer the ones that are overhead. But, you know, why pick one or the other? If it happens, it happens. Just enjoy it when you get to it. But I certainly like these a lot better when they're bright enough to take very short exposures. Although if you want individual pictures, the short exposures usually are pretty grainy. So you've got a trade-off between a lower ISO and a longer exposure, or high ISO and short exposures. You have to decide whether you want to make a movie or whether you want to just take still pictures. In the middle of the night, that band will often develop into something with some structure. This is one that's making a transition from a northern auroral display to one that's moving overhead. And it's usually fairly quickly that stuff there, suddenly those spikes start to reach a long way up and they smooth out. And this one's kind of blotchy, but that's because it's a bit of a longer exposure. It wasn't all that bright. So that some of the fine structures smoothed out during this long exposure. What's a long exposure? 10 seconds. So you should be able to get faster than that. Late night, when the auroral storm gets going, you see this one growing across the sky, but in this case, it's mostly green, which I find to be more or less the case. And there'll be some purple mixed in with it. These all have to do with certain ions that are going. This is taken from a little north of Stony Mountain, and we were late getting out. But look at how the activity increases. But always in the north, there's this curtain-like activity going on. And so these things, to watch them, you know, aurora can get tiring fairly quickly. And I'm talking after about this, you know, you're going into the second or third hour of this kind of thing. You say, well, I've had enough of this. But things happen, as you can see. It's fairly steady for a while, and all of a sudden something dances across the sky as some twist in the magnetic field comes your way. So it's a question of whether you're working the next morning, how cold it is, where you're located, and so on and so forth. It's almost like if we had a really big membership, we could have a northern Glenlee for watching aurora and a southern Glenlee for watching the Milky Way. I don't think that's about to happen. Here's one of the few times when I've been under the curtain here in Winnipeg. And you can see this is an early in the night one because it's purple on the top. Although there are ways of getting purple colors that don't involve being in the sunlight. It's a little bit to the west of the city, a little spot we found that had an old church in it. And with a fisheye lens, which I'm using here, it's always nice to fix it in such a way that you get some of the horizon around it. The power lines are definitely not what I like. But when you can get under the auroral oval, so you're looking straight up at it like this, you begin to see the twists and turns generated by the magnetic field a little better. And then, of course, this all-sky aurora, this is, it's characterized by a point in straight overhead that everything seems to radiate out for. That's where it gets its name, corona. Most commonly, this is the way we see it, with mostly greenish colors, sometimes with a little bit of purple in it. This is one that has more purple than most, so it mixes between green and purple. But when we do see them, they give you a taste of what is most common in the south, and also gives you a feeling for those early Greek and Babylonian description of the reddish sky and sort of thing. So you can see it kind of pulses between greens and reds, and some parts are green and some are not. I find this kind of aurora lends itself best to shooting video. You get to appreciate the motion a little more. This was taken a month ago during the Perseids from Toulon. And this is unenhanced. This is the way the sky appeared. The color was pretty incredible. And this is a coronal type of auroral outburst. But the mixture of red and green was really, it was an experience I hadn't seen before, to be able to put them both together. And the colors were visible, and not this. The camera, especially this was a filterless camera, so the red is enhanced in it. But the camera sees it in much more brilliant colors than the eye does. But the eye did see the red, did see the green. And what was also interesting about the night, later on in the night, there was mostly green aurora to my eyes, and there were patches that were dark. But when I took a picture of them, those dark areas were full of red, quite intense red. So the camera reveals so much more to you than your eye actually sees. You see and experience the aurora, but the camera tells you much more about what it is you're looking at. And then we get these steves. Now, in this picture, the lower part of the image is a night with aurora, but it's been a pretty good aurora, but now it's dying away. It's around midnight, 11 o'clock at night. And this unusual band, red on one side, green on the other side, appeared. And it didn't last very long, a little over half an hour, maybe 40, 45 minutes. But it's what they call a strong thermal emission velocity enhancement. And I think we all know the story of Steve. Some fellows in Edmonton were having a dinner party or dinner meeting with somebody who was an auroral expert, and they showed him this picture. And he said, I haven't seen that before. What's that? Oh, that's Steve. We didn't know what it was, so we just called it Steve. And so they later on had to go and invent this strong thermal emission velocity enhancement to match the name Steve. It's fascinating stuff because it's an ionospheric flow of electrons and ionized atoms. And the green part of it is what they call precipitating particles. That's the same sort of thing as causes the aurora, but the red thing is not. The red is a very high temperature area in the ionosphere, and the excitement of nitrogen molecules gives it that reddish color. And in the course of the night, this moved gradually southward, and you could see the fact that the green was above the red. They're not side by side, as you might think here. And later on, it developed into this kind of a pattern. And we weren't making a point of doing time lapse, so Judy put together these pictures. And then it marched off into Saskatchewan over a period of half an hour. And it was quite incredible. Meantime, there's this sort of modest aurora going on toward the north. But this is a sub-auroral event, meaning it's below the aurora. And by that, they mean at a lower latitude. So you might have the aurora here, and Steve is going to be overhead or close to overhead. And since then, I've gone back through my auroral pictures and identified 2 other places where I captured as Steve. Where do colors come from? Here we see some reddish colors on the bottom. This is taken from Beaudry Park. And the colors come from the molecules and atoms in the Earth's atmosphere as they're struck by these particles coming in from the sun. And when these atoms are struck, they can have several things happen. One thing is that if they're molecules, they get a lot more vibration. They pick up a lot more vibrational energy. That's the way molecules show an increase in energy unless they're completely split apart. For atoms, the electrons in the atom that are in orbit can be knocked off of the atom, or they can be raised to a higher energy level in their sort of, I'm going to say, orbits or path around the atom, the nucleus. And then, of course, they cascade back down. They don't like staying at this elevated energy level. They throw away their energy and go back down to the sort of normal basement levels where they typically lie. But the way they get rid of that energy is by emitting light. And depending on how they fall back from their energetic level to their ground state, as it's called, will depend on what colors of light. So if they make small cascades downward, they give off red light. If they give bigger cascade downward, they'll give off green light, and so on. And there's other colors too, but we don't typically see them in the ultraviolet. So in the case of green, it's a fairly typical cascade in oxygen atoms. And when you get red on the lower levels, it tends to be a mixture of nitrogen and oxygen. And when you see red in the lower levels, it means you get a particularly energetic flow from the sun, meaning that the electrons and ions are able to penetrate deeper into the atmosphere where they can encounter nitrogen molecules that are in greater density in the lower atmosphere. That's in contrast to those purple spikes that I showed you. So you can sort of see that here's the electrons in the top coming in, they're striking an oxygen atom, they excite it, and it gives off red light. Now, this is the one place you'll get red light in the upper atmosphere is when oxygen is excited. But more likely is a pathway on the right where the electron strikes the oxygen atom a little lower and gives off green light. And this differences in these red and green just depends on the cascade of these electrons as they're coming back into their ground state. And the reason you get red in the upper atmosphere is it's a fairly rare transition that takes a long time to happen on average. And by long time, we're talking tiny fractions of a second, or in this case, a fairly significant part of a second for the red light. Normally in the lower atmosphere, that oxygen atom collides with something else and loses its energy. It doesn't last long enough, but in the upper atmosphere, collisions are less frequent. So it has time to hold its energy for a brief period and then cascade down to give you the red. And you can see again, you can hit an electron with a lot of energy, hits a nitrogen molecule, not an atom, and that molecule will give off both red and blue light. We tend to see the red level, although it may have a purpley colored because it's also got some blue. And again, these are different cascades as these atoms return to the ground state. So here is just to emphasize what the eye sees and what the camera sees on these sorts of things. So if you want to go watch aurora, by all means do it. but if you've got a camera that'll take these pictures, use it. You can photograph with a cell phone. I experimented with a program called Astro Shader. It has one of the most important things for photographing aurora is that it's free. And so to me, that's it's a bit fiddly to use, and I did get pictures with it of the aurora. I think the newer iPhones and especially Android devices seem to be much better at photographing aurora than this was. I think an iPhone 11 or something like that. So I'm a little behind the times. And there I was telling you I was into AI and right up with it, and now I'm using an 8-year-old cell phone. But there's some pictures other people have taken, and you can't take the definition or color or anything like that as a reflection on the camera, just the person taking the picture. You do need a stable base. My case, I just rested it on the window of the car and let it point upward with the wide angle induced. Sometimes these cameras, you can't shoot wide angle if you have certain modes. Does it make a sound? Conventional wisdom says no. People have told me they do hear it. There are a couple of explanations. One might be just like you're responding to electromagnetic ripples. That's a little bit like swamp gas and UFOs. There's been a recent paper that suggests that the atmosphere responds to the electric fields a little bit and may end up giving some low volume sounds. The big thing is you have to record them, because you can record anything the ear can hear unless it's internal stimulation of the ear, not an actual sound wave. So it shouldn't be hard to do. Legends, well, a common one across the Inuit world. Okay, another AI image. No, not this one. I can't remember. Anyway, it's usually a game being played in the sky, a soccer game using the head of a skull, a human skull, a walrus skull, something like that. Played by people who've died, and it changes from place to place. These are based mostly on Baffin Island stories, but if you go over to the Western Arctic, you'll get a different story. Sorry, I didn't collect those when I lived there, but I was 18 years old, and who does anything sensible at the age of 18? Here we are, Alaska, souls of animals, their favorite animals dancing. These are not AI images. Don't whistle at the light. Don't play cat's cradle when the lights are on. You'll be taken up into the sky. But now the kids in the Arctic whistle at it for fun and sort of daring the northern lights to take them away. In Manitoulin Island, the Indian stories of the aurora are a little bit different than the Inuit stories. You can see here that revolves around a creator, and it's a little bit like the rainbow in Christian literature is a sign from God, and that's what's happened here. This is an AI generated image. So give me a bunch of Courrier de Bois sitting around a campfire watching the aurora. And I said, later on, when they gave me a picture, I said, no, make it a little earlier than that, 16th century. So yeah, AI is fun to play with, but to get really convincing images, you have to spend a lot more time giving instructions to these programs. And besides, after 40 tries, they stop letting you do it for free. So where do you find out? Well, you go to spaceweather.com. That's the one that most of us typically use. And they'll show you the sunspots on the top of the page. And if you scroll down, you come to the map that shows the level of auroral activity. And you can keep on going, scrolling down the page and get into the NASA predictions and actual measurements. So here's where you do if you want to see it. The main thing is to be dark toward the north, which means get out of the city and go north somewhere. You can go over to the northwest if you want. You can go over to the northeast, say out Dugald Road if you want. Up toward Lac du Bonnet, but not that far, just as soon as you get dark. If you go north on number 6 or 7, you tend not to get so dark. You get off to the side a little bit. If you really want to go somewhere, well, the 2A, B, and C give you some ideas. I would suggest you go as late as you can, and possibly after midnight in the winter, and even up to 1 o'clock in the summer. We like it in the equinox and when the pores are pointed, or the cusp is pointed toward the sun. Solar maximum and afterwards, well, that's certainly coming up now. Spaceweather.com will tell you when a CME is headed your way. And full moon, even last night's quarter moon low in the sky was a little bit of a detriment. But on the other hand, I've seen some really good auroras where the illumination of the scene is actually very nice. Birds Hill Park and Oak Hammock Marsh are a little crowded, and Spruce Woods Provincial Park, because it's a dark sky site, but you can find a good northern sky without going that far out. So, good luck. It's aurora season for the next 3 years. Thanks very much. Well, you're gonna ask me questions I can't answer, aren't you?
What was the name of that fellow that does these exquisitely processed solar?
Bill Bob,
Say it.
MILO FLAD, group mover, DRUCK MULLER. I probably didn't pronounce it right. Okay, who's Slavic and gonna tell me this?
I have a question. When I was in Antarctica during 6 months of daylight, I had sun dogs all day. 6 months of. Sorry, I have a comment and a question. When I was in Antarctica for a year, we had 6 months of daylight and it was all sun dogs, like the full thing. And then at night was 6 months of aurora. Yeah, just green and sometimes more active.
So you got pretty bored with both sundogs and aurora.
No, one time there was one so intense, I was walking, and it filled my peripheral vision, and it felt like I was in one of those gas creatures in Star Trek.
Okay.
And my question is, do you know what's the origin of the South Atlantic anomaly?
I don't know what it is. The South Atlantic anomaly is a place in the Earth's magnetic field where the magnetic field dips very, very low for South America. That's the South Atlantic. And it has to do with local magnetic fields, I believe, but the actual picture of it. It's actually a bit of concern because the astronauts in orbit, when they cross through this thing, get an extra dose of radiation, particle radiation from the sun. So it would be very interesting if it was part of their south to see if it had an impact on aurora, but I think it's a little too far north. But I could be corrected. I'm going to South America in a couple of weeks, so I'll get up.
Apparently they have to shut down.
Well, I was feeling a little sorry for those folks that went into 1,400-mile orbit the other day, just at the time the sun let go with the huge burst of radiation. I'm presuming that'll be all right.
I have a question. How did the Babylonians go see the there are very low that
That's true. The Babylonians lived pretty far to the south, but we do know that in a person's lifetime, like I've seen aurora from Nebraska. I know there are reports recently of the aurora in Texas. So you get into the northern part, especially into the Acadian part, which was, and that's AKKAD, not the way But you get into the northern part of the Babylonian and Akkadian Empire, that's certainly in comparable latitudes. And there were no slugs that were moving around and traveling too. Babylonian influence went long way to the north. Okay, well, we have a cloudy night tonight, so I guess we will go for the Aurora Oval. They were sort of looking at the possibility of another CME tonight. It's kind of moving with the weather that we have. But certainly, pay attention to what's happening. These next 3 years or so, we're going to be in for some really big treats. So keep your cameras ready to go. I know I've chased Judy out of bed at 5 after midnight to show her the Aurora Oval. We've gone out and had some pretty good auroras. You also have to be aware that just because it's red doesn't mean it's gonna happen, so you take your neighbor out with you and it's glowing red and nothing happens, you can look like a bit of a fool. You can be a fool to yourself, but you don't wanna be a fool to your neighbors. And I guess we're done.
Thank you very much, Jay. Actually, it was a better talk the second time around, darker also, because we saw it at the public event for Spruce Woods, and I think after about halfway through, many people started drifting off to take their kids to bed, so it was really interesting.
Yeah, the sun was still up on an outdoor screen.
Yeah. Mid-August isn't a great time to show aurora in the earth. Anyway, thank you all for coming to tonight's meeting. The next meeting is October the 18th, because the Bomber game is the week before. By then you'll be full of turkey and thinking about going out earlier in the evening to see the stars and the aurora and whatever's up, because it's dark when you finish the meeting. Yeah, it won't be dark quite that early when we get to the meeting.
And don't forget the U of M event.
Oh, yes, the U of M event on October 9-10. We would like some volunteers for that to help us out, showing the public whatever's up, the moon, Saturn, Jupiter, and a few darker sky objects later in the evening. So you can see me after the meeting, or you're welcome to join us at Boston Pizza, just over on Pembina. Yes, Vicky?
Say that meeting.
No, it's in this room. Yeah. I think that's all. Thank you for people who are on Zoom and for people who are here in person, and mix it up. We'd like to see everybody. Thanks so much.